Hello, today I'm going to introduce my project on the effect of surface roughness on nucleate boiling heat transfer. This study is based on a console simulation using an extended RPI boiling model. Here's a project background. In many industrial systems, especially in nuclear reactors, efficient heat removal is critical. Boiling heat transfer is widely used because it can transfer large amounts of heat. However, there are two main regimes. First one is nucleate boiling, which is highly efficient, and another one is film boiling, which is inefficient and dangerous. So avoiding film boiling is therefore very important in real industry. Here's the physics behind boiling. Boiling starts at nucleation sites. On the heated surface, on like the picture on the right, there are many nucleation sites on the surface, and the boiling just starts there. More surface roughness means more nucleation sites, and more nucleation sites means more bubble can be generated. This also means a higher heat transfer. However, if too much vapor being accumulated, it can cover the surface and reduce the heat transfer, even leads the nucleate boiling to film boiling. So that's not what we want to happen. The project question here first is, can surface roughness influence boiling behavior, and can it improve heat transfer performance? The most important one here is there an optimal surface roughness for maximum heat transfer? So through this project, we want to find most efficient roughness to maximize the heat transfer. The key idea is that the nucleation site density depends on the surface roughness. Well, we can find the information on the reference. There's a paper to showing this relationship. And the evaporation rate is related to the number of nucleation sites. To evaluate the heat transfer performance, we use a temperature difference between the hot surface and the fluid. A smaller temperature difference means better heat transfer. And this study is based on a console model for subcooled nucleate boiling using the extended RPI model. It is a multi-phase model that represents vapor as a volume fraction, and the most importantly, it does not really simulate the individual bubbles. The geometry for this model is 2D axis symmetric with a constant heat input. And also, I did some modification on the original model. I did not modify the model structure. Instead, I introduced surface roughness as a scale factor applied to the nucleation site density. So nucleation site density is proportional to a roughness multiplier. This allows us to study the effect of roughness without modeling surface geometry, which is an efficient approximation and simplification. And the parametric study was being used. We varied the roughness multiplier from 0 to 6. For each case, we analyzed 4 different terms. The first is gas volume fraction. The second is fluid temperature. The third one is hot surface temperature. And the last one, the most important one, is a difference between the fluid temperature and the water temperature. And let's move to the simulation result. The first is gas volume fraction. And as roughness, we can see here, as the roughness increases, the gas volume fraction keep increasing. This indicates stronger boiling activity. and there's a sharp increase being obvious after the roughness reaches around 2. We can see this range. For the fluid temperature, the fluid temperature changes only slightly. We can see the scale here on the y-axis. This means the overall fluid behavior remains relatively stable when the surface roughness changed. Move to the surface temperature. The surface temperature decreases initially as roughness increases, which indicates improved heat transfer. However, at high roughness, the wall temperature rises sharply. We can see here after 2, indicates a change in boiling behavior. Finally, for the heat transfer performance, we use the temperature difference between the hot surface and the fluid as an indicator of heat transfer performance. As roughness increases, this temperature difference decreases significantly at the beginning. The minimize occurs at roughness about 2. Beyond this point, the temperature difference increases dramatically. So what can we draw from the result? The first thing is we can clearly see 3 different boiling regimes. At a low roughness, boiling is weak and heat transfer is relatively poor. At moderate roughness, nucleate boiling is becoming stronger and heat transfer is maximized. At high roughness, the surface becomes vapor dominated and heat transfer deteriorates. The key insight here is that an optimal roughness exists. At a roughness about 2, heat transfer is the strongest. Beyond this point, the vapor covers the surface, which increases the thermal resistance and reduces heat transfer. Surface roughness increases nucleation size, which improves the heat transfer efficiency. However, too much vapor leads to bubble cover the surface. This creates a vapor layer and reduces heat transfer efficiency. So as a picture on the right showing here, when the surface roughness factor is 6, the maximum gas volume fraction is 94%, which means we can say it's almost not nucleate boiling anymore. It's almost film boiling. So the conclusion we can get from this project is that surface roughness has a strong impact on boiling heat transfer. There exists an optimal roughness that maximizes performance. Beyond that, heat transfer deteriorates due to the vapor domination. This project also have some limitations. The first thing is that the study does not model the surface geometry. The model uses a simplified multi-phase approach without interface tracking. Therefore, the results are qualitative instead of exact. So here is a reference for the project. And finally, I would like to sincerely thank Professor Dr. Wieland for his guidance and support through this project and the whole semester. As an international student, I was really surprised by his ability to provide a clear and effective help, even across different software language settings. His help has been extremely valuable. Thank you.